Hello everyone, and this is physics. In this video, I'd like to have another discussion regarding fluids. In particular, I want to talk about pressure at a depth using this equation. Now we've talked about, or I have made a previous video regarding absolute pressure and gauge pressure. So I'm going to do a little bit more regarding absolute and gauge pressures today. But before we get started, I need to set up my little tabletop. I'd like to do a quick demonstration, and then we'll go on and we'll have a look at this equation and how it is used. It is definitely getting crowded in my little space as I do these various demonstrations. And now I need some beakers. I have here a variety of beakers. You're all familiar with these. And this is a test tube. In each one of these, I marked a little line right here. So they are going to pour some liquid in them such that they're all at the same depth. And I made a measurement. And I measured, arbitrarily, I made a measurement here where there is a small mark in the glass itself. And I measured that to be from the tabletop 58 millimeters. And I have written that here, 58 millimeters. I'm going to put some liquid into these three containers. Water. In this particular case, I put some green food coloring into this bottle. And I'm going to fill, let's start with this one, with water, with food coloring. I'm going to bring it up to the 58 millimeter mark, I should say, 58 millimeter mark. Okay. Yeah, close enough. And I'm going to do the same with this bottle. Bring it up, and I put a blue line here to represent 58 millimeters. Fill this up. There we go. And I have here a test tube. Same thing. I put a little blue line on it to represent the 58 millimeter mark. And that's the height from the tabletop to that line. And it puts them in here. Oh, a little too much. For our demonstration, it's really not that critical. That's good. Now it won't stand up on its own, so I have this extra glass here to help me. Now you will notice I got three different types of bottles, three different shapes. And we're going to calculate the pressure at a depth. Pressure at a depth of these three containers. The shape of the container has absolutely no impact whatsoever on the pressure at a depth. In each one of these, I'm going to put a ball bearing. This is a long and involved experiment, isn't it? I'll put a ball bearing in that one. Well, I don't want to break the jar, so I'm just going to roll it down there gently. Ball bearing in that one, and I'm going to, there we go. Ball bearing in this one. You'll notice here that the height has raised a little bit. We're going to ignore that. And just simply go with the original 58. That's a topic for a whole other video. So in each one of these here, there is a small ball bearing down at the bottom. And what I want to do in this particular video is calculate what the pressure is at the top of that ball bearing as a result of the height of the water, which we have here. Now, as I said earlier, and the reason I have these three containers here, the pressure that's sitting down here at the bottom, resting on top of that ball bearing, is irrelevant, does not matter on the shape of the actual container itself. Okay, this one here has some ribs down the bottom. You're all familiar with water bottles. Has some various ribs here. Here is one that's basically rectangular or square in shape. And of course I have the little skinny test tube. The shape of the container is irrelevant. It does not matter whatsoever to the pressure at the bottom. Imagine you're going into Lake Ontario or any of the Great Lakes. When you first walk in, your feet are a couple of inches below the water. If the pressure was a result of the length and the breadth of the entire lake, well, that would crush your feet, but your feet don't get crushed. That's because the size, the width and the length of the lakes, or the size and the width and the breadth of these containers, has no impact on the pressure down at the bottom here where the bearing is. As you walk deeper in Lake Ontario or any other Great Lakes or any ocean, as you walk deeper, your feet are getting deeper and deeper and deeper into the water, and then you start to feel the pressure. And it's only a result of the height of the water above your feet, not the size and depth and breadth of the, or I should say not the size, the width and breadth of the lake. Only the depth matters. Having said that, I need to put these away, and we're going to calculate what the pressure is at the top of these ball bearings. I made some measurements already just to speed things up. I'm going to put these aside. And before I go forward, I have something else I'd like to show you. This is from a previous video. I have a question for you. I take this lid off. In here, how many fluids are there? If you see my previous video, at the bottom there is water. At the top here I have extra virgin olive oil, and on the top of that is air. And the question is, how many fluids do you see here? And the answer is, well, there are 3 fluids. Water is a fluid. It's a liquid, but it's a fluid. Oil is also a fluid, and so is air. So there are in fact 3 fluids here. And the air has pressure on it. That the air pressure is pushing down on the oil, and going down the oil has some density to it, and it is applying a pressure on the water beneath it. And then the water beneath it is applying a pressure at the bottom of the container. And that's what this equation here will solve. Pressure at a depth. The various different pressures, even with these 3 fluids. But we're going to just do the one. I will leave this as an exercise for you to do. Put that there. Now it's really getting crowded here. Hopefully I don't spill any of this liquid. Put you down here. I'm going to take this apart so we can see my board a little easier. Oh. I keep putting them away and they keep showing up. So let's have a look. I made some measurements, as I said, and I've taken some notes. P2, or pressure at a depth, is equal to P1, that's the pressure above the fluid, plus this is the hydrostatic pressure itself, rho GH. Let's have a look at the units of this. I'm going to scroll down. Now pressure has the units of a Pascal. Let's have a look at that. Pressure. Generally speaking, pressure is equal to force divided by the area. If I were to apply a force on this wall, the force, all forces have the units of a Newton. If I'm applying a force on the sides of this wall right here, and if I look at the units of this, so I'm applying a force on here, and the units of force, all forces have the units of a Newton. And the area, if I measure the area here in meters, and the area will have units of square meters. Therefore, pressure has the units of a Newton per square meter. Newton per square meter also has another name, and that is a Pascal, PA. And this is named after Blaise Pascal. Blaise Pascal. And when I use his surname in units, I just anglicized it and I called it a Pascal rather than a Pascal. But so all pressure has the units of a Pascal, Newton per square meter. Having said that, let's go to our equation for pressure at a depth. Pressure at a depth, or P2, is equal to the pressure on top of the fluid, pressure 1, plus rho GH. When I write this, I write the letter P with a small little stem on the top of it right here, and that's to distinguish it from the letter rho. So my P for pressure has a little stem here representing P for pressure, and rho does not. So that I'm able to distinguish between the two. So let's look at the units now of this. Now I just said that pressure has the units of a Pascal. So this has the units of Pascal. And pressure at 1 also has the units of Pascal. Plus, and this is not multiplied, it's important that you note this is addition. Rho GH. Sometimes I ask myself, why do I get myself into these things? Rho GH, let's have a look at the units of rho GH. Density, that's kilograms per cubic meter. And G, we know, has the units of meters per second squared. And H is the height or the depth. If I have my little beakers. H is that depth. Or you can call it height. If you're starting at the bottom, working your way up, it's height. If you start at the top, working your way down, it's depth. Either way, and it has to be in meters. Now we have meters. That's a Pascal, that's a Pascal. Looking at this, if I take this meter and I cancel it out with one of these three, that makes 2. So this becomes kilogram meter divided by meter squared second squared. Now we already know that a kilogram meter per second squared is a Newton. And I'll leave you to work this out. It is a Newton, it'll be in the numerator, and it's divided by meter squared. And a Newton per meter squared, we said earlier, is a Pascal. So all of this boils down to being just a Pascal. And that's a good thing, because this is Pascals and that's Pascals. This has to be Pascals in order to add these two terms together. You can't add apples and pears together. It's got to be apples and apples, peaches and peaches, etc. Having said all of that, now that we know what the units are going to be for this equation, let's actually use the equation and calculate the pressure at the depth, 58 millimeters. I'm going to draw the beaker here. A beaker, and it doesn't matter the shape of the beaker. It can be any shape at all. Only the depth is important. And I had the ball bearing down at the bottom here. And I said that the entire depth from the top of the fluid down to the bottom of the beaker, I said was going to be 58 millimeters. And I measured the ball bearing. It happens to be a 10 millimeter ball bearing. So that's 10 millimeters in diameter. Therefore, the fluid, I want to find what the pressure is here at the top of the ball bearing. That's what pressure 2 represents right here. P2 calculates the pressure at the depth, pressure at a depth right here. I'm going to calculate it at that point. Therefore, I need to know what the depth is at this point. Obviously, 58 minus the 10 will give me 48 millimeters. That is the depth that I need to know for our equation. 48 millimeters is not a base unit. You need to divide that by 1,000, change it into meters, and that becomes 0.048 meters. And that is the depth or the height that I am interested in. Having said that, I'm going to scroll down a bit more. And I'm looking for pressure at 2. Down here. Equal to pressure at 1 plus rho GH, and I am using fresh water. There are 2 ways to do this calculation, or there's 2 ways to determine what this pressure is. One is using absolute. The absolute, and the other is gauge. I'm going to do absolute first, and what absolute does is it includes the original atmospheric pressure. So here is that container yet again. And remember what I said earlier in the other beaker down here? There were three fluids: water, oil, and air. Well, there's a fluid up here, and that's called air. Air. And air is applying a pressure on all of us and on top of this water. All of these water beakers that I have has air on top of it. And that air is on here. It is applying atmospheric pressure on the top of that liquid, that water. Since we are going to include the air pressure, that becomes an absolute value. And that is P1. So looking at this is P1 pushing down here. Pressure 1, that is the atmospheric pressure pushing down on that water. Our ball bearing is down here, so I need now to find out how much pressure the actual liquid itself is applying on top of the ball bearing, including the air pressure. That makes it absolute. So putting in the numbers, pressure at 2 down here is equal to the atmospheric pressure, that happens to be, and I'm going to go down here a bit, 101,300 pascals is the atmospheric pressure. That's the pressure pushing down on top of the water surface, plus the density of the water, 1,000 kilograms per cubic meter. I'm running out of space, so I won't bother to putting in the units, times G, 9.81 meters per second squared, and times the height or the depth in base units, and that would be 0.048 meters times 0.048 meters. Therefore, pressure at 2 absolute. Pressure at 2 absolute, this means I am including the original atmospheric pressure, is equal to, doing all of this mathematics, I get 101,770. And the unit is a Pascal. 101,170.88 pascals. The last thing that I would do here at this stage is round this to proper significant figures. And where do we get the significant figures from? Well, it comes from the measurement. And that measurement comes from this height at which I originally measured using a rather crude instrument right here. And this is to 2 sig figs. Rounding this to 2 sig figs, then, would it make a heck of a lot of sense? So that would be technically improper to do. What I would need to do is go back to my measuring instrument, find one that will give me 5 or 6 decimal places, and then do the rounding to 5 or 6 decimal places. But right now, because I'm using this very crude measurement system right here of only 2 sig figs, I'm going to leave this as it is. Otherwise, if I round this, it won't make a lot of sense, because it'll look like it's actually less pressure down here than the atmospheric pressure is originally, and that just simply doesn't make sense. So I'm going to leave it as 101,770, which is a little bit above atmospheric. That was in absolute. Let's do the exact same thing now using gauge. And all we're doing with gauge is we're not including the original air pressure. Same equation, just not including P1. Pressure at depth, and we're going to do gauge pressure now. Now, the Canadian method of spelling gauge is GAU, and the British method is GAU. The American method, the Americans, they dropped out the U, so they simply call it GAGE, gauge. That's American, and this would be Canadian British spelling for gauge. So pressure at 2 is equal to pressure at 1. That would be, in our scenario, not always, the atmospheric pressure pushing down, plus rho GH. This is everything for the water, hydrostatic pressure of the water itself. Since we're using gauge, in terms of gauge, the atmospheric pressure is 0 gauge. So this drops out. 0 gauge. So pressure at 2 then reduces to just simply rho GH. Putting in the numbers now, and we're using fresh water. Density of fresh water is 1,000 kilograms per cubic meter, times G, 9.81 meters per second squared. And the height that I'm looking at is 0.048 meters. Multiplying this, pressure at 2 in terms of gauge pressure happens to be 470.88 pascals. So all I've done here is eliminated the atmospheric pressure. If I go back a little bit, could have taken a shortcut because in our scenario right here is on the simplest form. The original pressure at 2 is 101,770. If I were to subtract from that minus the original atmospheric pressure, because I'm only talking a gauge, which is 101,300 pascals, make that subtraction and the answer will be 470.88 pascals. And 470. All I've done here is remove the original atmospheric pressure, and this becomes gauge. Now I should back up here. When we're doing this, in terms of gauge, it should be written down. Here's my answer, and then we should write down the word gauge here somewhere. Or pressure at 2, gauge. Somewhere in here we need to qualify to tell whoever is doing the reading of this particular calculation whether I'm doing the solution in gauge pressure or in absolute pressure. But I already did that for absolute here earlier, as you can see, so just need to write down either it's gauge or absolute. This equation can be used here. There are 3 fluids here. If we look at this, and I'll leave it to you to do any calculations. We have pressure at 1, that would be the atmospheric pressure. Then we can calculate what the pressure is here at the bottom of the oil using the density of the oil. And then once we calculate that one, that becomes the new P1. That's the new P1 acting on the water beneath it. So we then do the same equation again using this one, that new pressure will be calculated here as P1, and then calculating what P2 is here at the bottom. That would be for absolute if we want to include the air. If we don't want to include the original air pressure, then it becomes the gauge pressure. In the same equation, P2 is equal to rho GH of only the oil. That new P2 that you found here becomes the new P1 for the next equation. And then we can use that one as P1. P2 is equal to P1, that pressure, plus the depth. Again, I will leave that one for you. And this is physics.